All right. So let's take a look at the opening exercise answer here. So I have the two equations ready to go. They're graphed now. Notice there are two solutions. So I'm hoping you did second calc, option 5, and you're able to find the first answer, which was negative 1.39. What does it ask us to round to? 1,000, 3 decimal places. So we have x equals negative 1.392. Thanks, Sydney. And we also have x equals whatever this other one is. Second trace, option 5. Scroll way over here to the other one. Not that far. Enter 3 times, and we get 1.686. Easy enough. Questions on the opening exercise? I hope not. If they are, it's okay. No? Okay. So let's talk about graphing. So in the last 2 lessons, we had some kind of graphing problems where we had these odd things happening on our graphs. This one I have it all scaled out for you. So we just have to kind of look at a couple things. So first things first, what is the asymptote line? We should know that just by looking at the equation. What's the line this graph is going to approach but not touch, Oliver? Negative 6. So the asymptote line is y equals negative 6. So if this is 100, each one of these boxes are worth 20. So negative 6 is going to be this like weird, very small line like that. Oh, no. That would be positive 6. Negative 6 isn't even going to be on here. It's going to be down here somewhere, right? So if we want to go ahead and graph this, we could go into our graphing calculator, go into y equals, and type it in. So you should type this in with me. 0.85 to the 2x and a minus 6. And I'm going to change my window since they gave me the graph paper. 0 to 10 for x and 0 to 400 for y. So I see what I see. It's going to look like it's asymptotic to the x-axis, but it's actually, we know it's going to negative 6. And then we could go ahead and start my graphing. Right, go into our table. 394 is going to be really close to 400. 283, so this is 100. 1, 2, 3, 4, 5. This will be 200. 1, 2, 3, 4, 5. That would be 300. So 280-ish is somewhere around here. Again, you're just estimating these points. 202, so a little bit above 2. 144, somewhere right about here. Again, just an estimation, nothing crazy here. 100. You should see it should follow like a pattern here. That's exponential. 72. So this is 20, 40, 60, 80. 70 is in between 60 and 80. So put it there. 51, 20, 40, 60, somewhere in between 40 and 60. 35, 20, 40, so somewhere close to 40. If we scroll down a little bit more, so we got 23, 15, and the last one is 10. So to give you some background about this, so this question was on a Regents exam, and they didn't ask us all this stuff on the bottom. They just asked us to state the equation of the asymptote. A lot of my Regents kids put the x-axis because that's what it looks like from your graph. But if you go into your table of values, you see that it's actually going to keep going down. It's going to cross the x-axis. And from what Oliver already told us, from what we know about the equation, we already know the asymptote line is negative 6. So the y-intercept was 0, 394. Asymptote is y equals negative 6. It's decay because it's decreasing. As the x values increase. Right? As we look at this graph from left to right, it's going down. Now, one of the things that we're going to transition to in Lesson 8 is in Lesson 8, we're going to start looking at real-life examples of how exponential functions can be used. A lot of them are going to deal with money and these special types of equations that we can have growth for, like half-life of a substance, and we're going to do a bunch of stuff like that. Before we can do anything like that, we need to talk about the algebra that's involved in it. So, on the next page, there's some algebra here that we're going to do. We're going to basically use the ideas of exponential functions properties to put all of these into a form where we know an a value and a b value. The a value is always going to be your y-intercept in this form, and your b value is going to determine if it's going to be decay or growth. Remember, if the b value is between 0 and 1, it's getting smaller over time, it's decay. If your b value is more than 1, it's going to be growth over time. So looking at these equations, I can't determine right away if it's growth or decay until the exponent is just x. Because sometimes the exponent will affect whether or not the base is going to be more or less than 1. So looking at f of x, if I was to rewrite this function using my properties of exponents, I can rewrite this as f of x is equal to 5 times 1.03 to the 4th power to the x. I'm basically just undoing the multiplication of the exponents. Now, if I simplify that, if I plug in my calculator 1.03 to the 4th power, I'm going to get some decimal. So I can rewrite this function as 5 times some decimal to the x power, 1.03 to the 4th power. I should be on the main screen here. 1.03 to the 4th power, and we get 1.255 dot dot dot. For all of these problems, if we have a decimal that's continuously going on forever, or a really big one like this, 4 decimal places is plenty. So we call that 4 significant digits, essentially. So we'll say 1.1255. Now, since the exponent's x and only x, I now can look at the base and say that's more than 1, making this growth. So if I was to do g of x and follow the same properties for g of x, I'd say, well, g of x is equal to 2 to the negative 1 to the x. Again, I'm just undoing the multiplication there. 2 to the negative first power is 0.5, meaning this is decay. So without doing this, if you just looked at it originally saying 2 is bigger than 1, it's growth, that's wrong. Right? You have to take into consideration that the exponent is changing the base as well. Try the last 3 yourself. If you want to check they got h of x right, it's up there. So KFT is a little bit tricky. To break apart the product that's in that exponent, it's a product of 1 over 8.02 and t. So if you put in 1.082 as the fraction there, the 100 doesn't change, but this base becomes 0.9172 to the x, meaning this is the k. Try P of t if you didn't get there yet. If I was you, I'd start by adding what's up in that parenthesis, make that easy for yourself. And we get growth for P of t as well. Questions on number 2. Easy. Try number 3 yourself. Explain why the function below represents an exponential decay function using 3 different methods. Holy smokes, what are our 3 methods? What's one of them, Oliver?
Algebraic.
Algebraic, so the same process we just did above. What's another one? How else could I determine if something's decay or not? Taylor? Just graph it, see what it looks like. Is it going down or is it going up? What else could we do? That's really the only 2 methods I would use, to be honest with you. Mr. Hines got a little crazy here and wanted 3. The third method would be to plug in 2 different values. Plug in like the t value of 1 and the t value of 6, and see did it go down or up from 1 to 6. Okay? Don't do the 3 methods. I just want you to look at it graphically first. Do that one first. Do you think it's decay or not from your graph? Then try and do what we just did above to try and make it so that you can get your base as a number that tells you whether or not it's growth or decay. The graph's going to be a little funky, so just bear with it. All right, so I played with my window a little bit for the graphing part. Here's a window I kind of came up with. I'm not really sure how many x values I need, so I played with it from anywhere from 100 to 10,000. 250 kind of worked out decent enough. The y values were where we had issue here because the starting value is 1,000 and it's either going to go up or down from 1,000. I made it a little bit below 1,000, a little bit above 1,000, just to determine is it going up or down. That's all I care about, right? I don't care if it's going to be show a perfect exponential function or not. So by changing around your table here a little bit, you can see that it is going down. Another thing you can look at in your table of values as you progress up with the x values, the y values are slowly going down, right? Very slowly going down. So that's the one way I'd explain it. The second way, the algebraic way, would be me taking this a of t function and rewriting it so that the 2.172 is to this negative 0.693 over 1590 number, so that the exponent's just t. If you did that algebra like we did above, we wind up having 0.9996 ... to the t power here. That's super close to 1, which is why it's not really coming out as a nice exponential looking graph, because it's almost a straight line, right? The closer that base number is to 1, the closer the whole thing is going to be to just being a straight line across. Which is why your y values are in fact changing, but they're changing super slowly. The rate of change of this function is not going to be very big, right? A very small rate of change. Easy enough? Questions for me? All right, let's take a look at number 4 on the next page. So on the next page, it says the value of a certain small passenger car based on its years is modeled by V of t. So V of t is the value. We should know as soon as you buy a car, the value of it is going to depreciate or go down over time. Not many cars reappreciate value at the end, right? We don't all buy, 1956 Corvettes. Zach has to take out a loan to purchase the passenger car. His loan amount has to be paid back. So what you're getting there is a function which represents the number of dollars and time and years of the unpaid amount of his loan. So we have a car value, we have a loan amount. So looking at this, the car value starts at a higher value than Zach's loan amount. So what that means is Zach probably paid a little bit of the car's value up front and just had to take out a loan for a little bit less than that. Since the larger of the two numbers is close to $30,000, when I start making my table here and look for my graph, I don't want to make the top number $28,482. That would make it virtually impossible for me to scale my y-axis. So I'm actually going to make my y-axis go up to 30,000, meaning each box is worth about $3,000. Now the interval is telling us to only graph between 0 to 5 on the t-axis, or the x-axis in this case. So I have 20 boxes, so if I make each box worth 4, I can graph the interval from 0 to 5. There was an interval on your trig test when we did your blood pressure question. It said from 0 to 2. A lot of people didn't know what that meant, right? So I wanted to make sure that I revisited intervals here, right? So if I'm saying graph something over an interval, I want you to graph for that interval and that interval only, right? So if you were to graph to 6 or something like that here, that would be wrong. If you were to graph up to 5, you'd be wrong. So here's what I want you to do. I want you to plug into your graphing calculator the two functions, and I want you to try and graph them. Okay, try and estimate. It's going to be all nasty decimals. Just do your best to estimate where each one is, remembering that each box vertically is worth 3.
Mr. Servino?
Yes, sir.
Isn't each box worth 1,500 because there's 20 boxes?
Yeah, every 2 boxes is 3,000. Thank you, Oliver. Bless you. And once you have it graphed on your paper, graph both of them in your calculator at the same time and see if you can set your table there or set your window there to find the intersection point. That's basically what it's asking you to do right below your graph. So I'm going to make my window 0 to 5 and 0 to 30,000. So I'm going to see the same thing that I should see on my paper. Noticing they intersect somewhere between 1 and 2. The graphing is just a pain in the butt. It's not really the hardest thing to do. It's a pain to count by 1500s, right? All right, so if I want to go through here and find this intersection point, I'll hit second, trace, intersect, scroll somewhat close to it, and hit enter 1, 2, 3 times, which gives us 1.37. So when it asks us to determine when the two functions are equal to each other, right, we would say when t equals 1.37. Now, what this means in the context of the problem is it's going to take 1.37 years for the value of the car and the amount left for Zach to pay off on his loan to be the same. So initially, his car's value is more than what he pays off on the loan. After 1.37 years, the loan amount is actually more than the car's value. So he owes more to the bank than what the value of what he borrowed was to buy, which is his car. I wish my wife saw this because she does this all the time when she buys a new car. She trades her car in when the value of it is less than what she owes still on it. Not a smart move. Okay? So what they're asking here when it says interpret the meaning of the context of the problem is this is when the car's value is the same as the remaining payment on the loan. Now, the last question asks us to do something slightly different. It says Zach takes out an insurance policy that requires him to pay $3,000 deductible in case of a collision. Zach will cancel the collision policy when the value of the car is equal to this deductible. Right? If I have a car that's only worth $3,000, I don't want to have this insurance policy anymore. So I want to figure out when is the value of the car equal to $3,000. So to do that, I'm going to plug in v of t, which we already have in our calculator as y1 or y2. And I'm going to put 3,000 as y2, or the other function. So when I go into my calculator here, the value equation is the first one I have typed in. So I'm going to clear the loan equation and just make it 3,000. Now, if I hit graph, I don't see an intersection yet. So that means I have to change my window to have more x values. Maybe go out to 10 years, right? The car value might take a while before it hits that 3,000 mark. To use the intersect feature in your graphing calculator, you must visually see the intersection on your screen. If you don't, it won't work. So if I hit second, trace, intersect, it's going to be pretty close anyway. It takes about 5.18 years. So on the bottom there where it says like to the nearest year, right? So it would be 5 years for the value to get close to $3,000. Questions? Questions on anything we did today in lesson number 7? Yes. All right. that's all I have for you today. So you can work on your homework assignment. Like I said, a kind of quick lesson. If you were a little bit confused about what the graph looks like for number 4, I do have it drawn out here on paper. You can borrow mine if you want to see where my points are. I know it was kind of hard to follow on the screen there. Okay.